Okay, it's great to have Chen here, returning back to IS from a couple years ago. He's now at Columbia and is going to talk to us on non-negatively weighted counting CSP.
I'm just fixing something for you.
Okay. Okay, so I'm really glad to have this opportunity to talk here. And first of all, this is a joint work with Jingyi Cai and Pingyan Lu, and the work here is mainly about dichotomy theorem for counting CSP, and CSP stands for Constraint Satisfaction Problems. And I think it's one of the most important classes of problems studied in TCS and many other fields. So in TCS, I think there are mainly three directions or aspects we look at these problems. The first one is decision. Given the CSP, is there a solution that satisfies all the constraints? And in 1974, Schaefer proved a dichotomy for all the CSP with Boolean domain, the decision problem. So he showed that every decision problem with domain size 2 is either in polynomial time or NP complete. And then in 1908, Federer and Vadi have this very nice conjecture on all decision CSP. Says that every problem should be either in polynomial time or NP hard. And this was proved by Bulletoff for domain size 3, but for larger domain, we don't have a proof yet. And the second direction, I think, is one of the most active research area in the past decade. So this is about optimization. Instead of finding a solution that satisfies all the constraints, we try to find a solution that satisfies as many as possible, or approximately as many as possible. And this consists of a big bulk of research in both complexity theory and approximation algorithms. So today I'm going to talk about the third direction, counting. So we count the number of solutions that satisfy all the constraints. And we will also generalize the problem to the weighted version. And as you will see, which I will come back to this point later, that this is one of the examples where a proper generalization actually gives us a much simpler resolution of the question we're interested in. So here is the definition of counting CSP. So we have capital D domain set, and you should also always consider this set to be something constant. So D is maybe 2 or 3 or 4. Given this domain set D, we say gamma is a constraint language, an unweighted constraint language if it's a set of predicates. And an instance of the CSP, the counting CSP, defined by gamma is basically a set of variables x1 to xn, and you can apply the constraints, the predicates, in any way you want over any subset of variables. And of course, this defines for us an unary relation. Okay? An assignment in this relation if only if all the constraints are satisfied. And given such an instance, in this counting problem, we need to count the number of solutions. We need to compute the cardinality of this relation R. And this is an interesting class because there are a lot of problems you can formulate as a counting CSP. For example, if you look at counting 3 colorings of a graph, you can just set D to be domain size 3 and gamma to be the theta to be the constraint that I not equal to J, and this gives you the counting 3 coloring problem. And for counting independent sets, you can let D to be this domain with 2 elements and theta to be this constraint, and it gives you counting independent sets. And of course, we can express number 2 sets and 3 sets, and we can formulate them as counting CSPs. But we can, more generally, we can define this non-negatively weighted counting CSP. So now we still have this domain D, but now a non-negatively weighted constraint language is a set of functions, okay? Non-negative functions. And similarly, an instance of this problem is just a bunch of variables, and you can apply these functions to any subset of variables in any way you want. And this instance would define for you an unary function, capital F, and it's just the product of the function evaluations. So in this case, given any assignment x, f of x is just the product of f1 of x1, x2, x3, and f2, x2, x3, x4, and so on and so forth. It's the product of all the constraint functions. Yes.
So RIs are the arities of
Yeah,
the
RI is the
relations,
arity.
So you have, say, weighted relations.
Yeah, you can have
Zero,
an
1,
arbitrary
right?
arity, yeah. But they're all considered to be constant. It's in the language. Oops, sorry. So here we're given such an input instance. It defines for us an unary function, capital F, and we need to compute the sum of f over all possible assignments.
So in the usual weighted CSP formulation, you'd get you'd be adding instead of multiplying
Right.
weights. And so
Right.
here you're multiplying and then adding.
Yeah, that's one difference from like studying optimization when you have weighted CSP. So here we multiply the weights and then sum them together.
So this way you count the number of assignments that satisfy all constraints.
Yes, I mean that's one.
Right,
If
yeah.
F has 0, 1, certainly.
Yeah. So in particular, if all these little f's are 0, 1 functions, then this comes back exactly to the unweighted case. So, so here is the main result. We showed that given any domain set D and any non-negatively weighted language, the problem it defines, the counting problem it defines is either solvable in polynomial time or shall be hard. Okay. So one thing I would like to point out is this theorem works for non-negative and algebraic numbers. But in the talk, I will just say non-negative numbers. And although we believe that if the numbers are given in an appropriate representation, then we should be able to extend the theorem to, for example, including numbers like e or pi. And the theorem, normally all such kind of theorems are proved by finding an appropriate tractability criterion. And I think half of the work is to find the right criterion. And as you will see, a criterion is just a well-defined mathematical property over the language. And the hope is that once we find the right criterion, we just show that if the language satisfies it, then we give a polynomial time algorithm. And if it does not satisfy it, we show that the problem is shall be hard. And in this way, we can get a dichotomy using this tractability criteria. And also, we showed that this problem, if we're given this language as the input, so now the language is not a constant, but it's an input, then the problem of deciding whether this language satisfies this criterion or not is in NP. So it's not that hard to decide whether a given problem is in polynomial time or shall be hard. Okay. But I think I will not have time to cover the decidability part, but we will focus on the dichotomy theorem. So the first thing I want to show you is this tractability criterion. But I think it would be better if we had very brief review of preferred results. Because in this way, you can see when we move from more restricted classes of problems to more general classes of problems, how this tractability criteria also evolves, and and it turns out that our tractability criterion is actually more succinct compared to some earlier works for the more restricted class of problems. So the first special case is also called counting graph homomorphisms. And this is really a special case because you only have one single constraint or function, and this function is binary over two variables, and it's symmetric. It's non-negative and symmetric. So normally we express this function as a d by d matrix, where d is the domain size. And there is this sequence of 4 papers. The first one gives a dichotomy for all the symmetric 0, 1 matrices, and then extended to symmetric non-negative matrices, and then matrices that are essentially acyclic directed graphs. And then last year we get dichotomy for all the non-negative matrices. But the only one I want to describe more closely here is the one by Bulletoff and Grove, because it's a very useful dichotomy, and it gives you it solves the problem for all the non-negative and symmetric matrices, and you will see that the tractability criterion is very simple.
So non-negative means that every entry is non-negative?
Yeah, every entry is non-negative. So you have symmetric non-negative matrices. Okay. So the tractability criterion is the following. If this matrix A is a diagonal, block diagonal matrix, and every block on the diagonal is either block rank 1 or looks like this. It's a 2 by 2 block diagonal, and this matrix B is also rank 1. So all the tractable matrices look like this. You have all these blocks, and every block either is completely rank 1 or has 2 off-diagonal rank 1 blocks. So these are the only tractable cases, and if your matrix does not look like this, then it's already Sharpie hard. And for these two, the reason I would not be able to describe them is because the criterion becomes much more involved. But we also have a lot more new tractable cases. For example, this 8 by 8 matrix is not symmetric, but it needs some work to see, this actually gives you a tractable, gives you an algorithm in polynomial time. So then in 2008, we have this big jump, and Bulletoff gave a very powerful and sweeping dichotomy for all the unweighted counting CSP. It turns out that his proof uses a lot of very deep structural theorems from Universal Algebra. And the tractability criterion of Bulletoff is this notion called congruence singularity, which is described using the language of Universal Algebra. And unfortunately, I know very, very little, almost nothing about Universal Algebra. So, yes?
Should also give a comment. So basically his criterion is that you need something like, say, linear system of equations in order to be able to solve the counting problems, say, like tooling or similar. So basically it's just a sort of formal generalization of this if it's unweighted, and if you give weights, then basically you should avoid all non-trivial weights. Say,
Yeah.
if you have just tooling times tooling, so you have a 4-element domain was just the tuples which coordinate 0 and 1, then you shouldn't have something like one has weight 2 and all the others have weight 1. So that
Yeah.
leads to any matrix of rank greater than 1.
Yeah.
But it basically only says that you need something like a linear system of equations, and the weight should be very non-trivial.
Yeah, the weight should be really non-trivial. Yeah, we will see.
Formally, it's quite unreadably stated, but it says basically that what else is non-trivial is too sharply complete.
Yeah. So one of my courses, Jingyi Cai is always the go-to guy if I have any question about universal algebra. So.
Well, they should write their papers in a way that it's not so easy to read as you prove too many things. They defend themselves this way.
Yeah, but fortunately, last year we got this alternative proof of Dyer and Richardby. So they proved the same dichotomy theorem for all the unweighted counting CSP, but the proof is considerably more direct, and notably they use very little universal algebra, and what it looks much better is they, at least for me, it looks much better because their tractability criterion is, as you will see in the next slide, is essentially a very combinatorial criterion. It's related to these two notions of strong rectangularity and strong balance. And later you will see how our tractability criterion is obtained from these two notions. So let me just introduce some very simple notation for non-active matrices. So we say capital M is first of all, it's a non-active matrix, and we say it's rectangular if you can permute the rows and columns so that it becomes block diagonal. Okay? And we say it's block rank 1 if it's rectangular and also all the blocks are rank 1. And now here comes this notion of strong rectangularity. Essentially, this condition says that if the language gamma satisfies this property, then there should be a large set of matrices that you can derive from this language, and all these matrices should be rectangular.
So before you were describing things in terms of these graph homomorphisms, and it was natural to think of the constraints in terms of matrices.
Yeah.
So why, for general counting CSPs, are you also using matrices?
Yeah, it's because you will see the flavor of all these conditions is that, for example, you have this input instance R, which is over, let's say, n variables. Then you try to partition the variables into 3 parts. And you put, let's say, the first part of the variables, you define a matrix whose rows are the assignments of the first part, and the columns are the assignments of the second part. And let's say you count the number of the third part assignments that can satisfy the whole assignment. So this way you get a matrix. And it turns out that all these matrices should satisfy some really nice property. And on the other hand, later we'll see that we only need to look at these matrices. If these matrices give you some really nice property, then you can use it, all these properties, to compute it very efficiently. Yeah, so it turns out you only need to deal with matrices. You never really deal with arity 3 or 4. So here is the definition of this strongly rectangular. We look at, we pick any instance. We pick any CSP instance, and it defines for us a relation R. And then we partition the variables in any way you want into 3 parts. And let's call the 3 parts U, V, and W. And this defines us a matrix where the rows are indexed by U and the columns are indexed by V. So it's a D to the K but due to the L matrix. And the entry of MUV is simply the number of W such that UVW is in the relation. So we say gamma is strongly rectangular if all possible matrices capital M construct in this way is rectangular. So this is a very, very strong condition because it's over all possible instances and all possible partitions. But we can show that if, first of all, gamma is not strongly rectangular, then the problem is already sharply hard. So at the end of the talk, I will have one slide explaining, hardness proof for theorems like this, because it turns out that the hardness part is normally the simple part. Normally, you can very easily to show certain things must be satisfied, otherwise it's sharply hard. But the really difficult part in proving the dichotomy theorem is to show that all the rest is easy. You need to give an algorithm for all the rest of the problems. So it turns out that once you have this strong rectangularity, you have very strong properties about the problems. So first of all, in the language of universal algebra, if you satisfy strong rectangularity, it's equivalent to having a Malchev polymorphism. And also, it turns out that if the language is strongly rectangular, then there is a very efficient algorithm for the following, what I call the witness problem. So the problem is, again, you're given an instance of the CSP, and you can fix a subset of variables in any way you want. For example, I fix x1 to be a1, x2 to be a2, x4 to be a4. I can fix a subset of variables in any way I want. Then I ask whether there is an assignment for the rest of the variables so that this assignment is in the relation. This assignment satisfies all the constraints. And if it exists, you also need to give me such an assignment. Okay, so this is a very difficult problem for general language gamma. But it turns out that if your gamma is strongly rectangular, then you have a polynomial time algorithm for this problem. And in particular, if I do not make any restriction, then it means this algorithm would give me a solution if it exists, and would tell me there does not exist a solution otherwise. But it turns out that even with this very strong witness algorithm, it's still not enough to guarantee that the problem is can be solvable in polynomial time.
Any problem in P would have that property, like so counting matchings or too sad or something like that.
Right.
Yeah,
It's not
particular.
Yeah. So it's not a surprise here. So we have a lot of examples which is strongly rectangular, but it's sharply hard. So it turns out that we need a little more, some condition stronger than strongly rectangular. And this is the notion used by Dyer and Richardby called strong balance. So again, we pick any instance, and now we partition the variables into 4 parts. So U, V, W, Z. And again, the matrices are indexed by U and V. And we count the number of W. The UV entry is we count the number of W such that there exists a Z so that UVWZ is in the relation. Okay. So if you compare this with strongly rectangular, we have this existential quantifiers here which do not appear in strong rectangularity. And also we require these matrices to be not just this should be block rank 1. We require these matrices to be not just rectangular, but they have to be block rank 1. All the blocks have to be rank 1, and the entries should satisfy some equations, like all these rank 1 properties.
So for non-square matrices, what is block diagonal? It's
it could be something like this. So you may have a matrix which looks like this, and by block rank 1, you can permute the rows and columns so that all these blocks are rank 1. And the reason I draw this matrix in this way is later we're going to deal with a lot of matrices which have exponential many rows but constant many columns. So
if it's not strongly balanced, then it will be sharply.
Yeah. Yeah.
Is it clear following this existential condition?
this one is not that simple, right? Because of these existential quantifier, you need to do something like interpolation to get the reduction. It's a little. And it turns out this strong balance is the right tractability criterion for unweighted counting CSP. And they show that if it's strongly balanced, then they give a polynomial time algorithm. And if it's not, then it's sharply hard. And it also turned out that this is equivalent to the notion of congruence singularity, which should not come as a surprise. Because if you can find proof to dichotomy with different, then something terrible happens. So now we try to extend all these results to a more general weighted setting. And the first idea is what would be the right tractability criterion. We know that this strong balance is the criterion for unweighted case. So can we simply extend it to this weighted setting? And the first problem here is we don't know how to deal with the existential quantifiers. Okay? So this is the definition. This is the definition of matrix M in the unweighted setting. So here we count, how many W we have, and this can be easily replaced by, for example, sum over all possible W's. But the only thing we don't know how to deal with is this existential quantifier. There is no easy way to introduce existential quantifiers in the weighted world. But the use of existential quantifier is very, very natural in the unweighted setting. It's very well defined, and it's used a lot of places in Universal Algebra. And also, the use of these existential quantifiers is crucial in the algorithm of Dyer and Richarby. So let me explain this sentence a little bit. So suppose you have a condition without existential quantifiers. This gives you some weaker properties about this language. But in the proof, in the algorithm of Dyer and Richarby, they need to have the property that even if I put existential quantifiers, then the matrix I get is still guaranteed to be block rank 1. Okay? They use this property almost everywhere in the algorithm. And without these existential quantifiers, it's not clear how the algorithm can still work. So the first idea we had is really a simple observation is, what if we just remove these existential quantifiers? Would this really gives you a property that is strictly weaker than strong balance? So we define the following notion of balance for this language gamma. So instead of partition the variables into 4 parts, we have these 3 partitions. And now we just count the number of W so that UVW is in R. And we say it's balanced if all such matrices are block rank 1. So see, now we don't use the existential quantifiers anymore. And it comes as a surprise that we can actually show that it's equivalent to strongly balanced. First of all, strong balance, of course, implies balance. But we can also show that if gamma is balanced, then it is also strongly balanced. So 2 implications is that, first of all, it gives us a more succinct criterion for unweighted number CSP. On the other hand, this new notion of balance can be easily generalized to the weighted world. And the hope is that this would be the correct tractability criterion for the weighted setting. So we can similarly define the notion of valence for weighted constraint language, L. And again, we pick any instance of this CSP L, and we partition the variables into three parts, U, V, W. And we look at this matrix where we sum, the U, V entry is the sum of F over all possible W's. Okay. This is just a way to replace the counting of W's. And we require that this matrix is block rank 1. All matrices that can be constructed in this way is block rank 1. And again, the harness part is easy. You can easily show that if it's not balanced, then it shall be hard. I have a slide at the end of the talk, but if we have time, we can talk about the harness part a little bit. But the really difficult part is, suppose your language is balanced. Suppose I guarantee you this language is balanced. How can you design a polynomial time algorithm for this problem? So there were two kind of simple but very useful ingredients of this algorithm we give. The first ingredient is, remember what is this capital F? This capital F is defined by an input instance, and it's the product of all these constraint functions. But it turns out that if the language is balanced, then we have a much more succinct representation for this function capital F, which we call a vector representation. So let's say F is an ordinary function. Then these R vectors S1 to SR is a vector representation. If you take any tuples, R tuple, and as long as f of x is positive, you can always compute f using these vectors. It becomes the tensor product of these vectors, and they agree with f at every place where f is positive.
So I see. So you've you've represented the entire r-dimensional tensor of f as the outer product of these r vectors.
They agree at every place where f is positive.
Oh, and for where it's 0?
It's not. So the idea is to look at this block rank 1 matrix. So suppose I tell you, let's say this is a block rank 1 matrix. Then clearly I can replace every block by two vectors. The tensor product of these two vectors are exactly this matrix. Mm-hmm. Then I can combine these three vectors and these three vectors, so I get two bigger vectors. And their tensor product agree with this matrix every place where it's positive. So we can show that if the language is balanced, then you can actually find a vector representation for every constraint function in the language. Okay? In particular, if you have a binary function, for example, in the language, then the condition of balance tell you that this function has to be, first of all, block rank 1. So you already have a vector representation. But for higher arity, you need to do some simple induction. And so now we can assume that every function in the language already comes with vector representation. And then you can show that now we're given an input with n variables, then we can still compute a vector representation for this n-ary function very quickly. Okay. And the idea is very simple, so I can describe it here. Yeah, the construction also tells you it exists. It always exists.
Sorry?
It always exists, and you can find compute one very efficiently.
This is if L is
Yeah, if L is balanced.
What's the hypothesis?
If L is balanced. Yeah. Because if it's not balanced, it's already Chapuis-Hard. So the idea is at the beginning, we don't have any constraints. So f is the all-one function. Then we can just set the vector for x1 to be the all-one vector, set all the vectors to be all-one vectors. So this clearly gives us a vector representation. And now suppose you have the first constraint f comes in. We know the language is balanced. So this function has a vector representation. So let's say it has sf1, sf2, sf3. Okay. Then we just update this vector to be s sub f1, this vector to be s sub f2, and this to be s sub f3. Okay. And now suppose the second function comes in. Let's say g. And again, g is a function in the language, so it has a vector representation. Let's say sg1, sg2, and sg3. And you can just replace, for example, this vector by the Hadamard product of these two vectors coming from f and g. And you update all the other coordinates in the same way. And you look at all the constraints one by one, and finally you can show that all these vectors you get is actually a vector representation of capital F. So now we can assume that even for this input, we already have a vector representation. So everything looks really nice so far, because if I tell you that for any assignment, this capital F is positive, then we can rewrite this exponential sum to be, this product of sums, which can be easily evaluated. But the problem is there were a lot of hosts. By host, I mean an assignment x such that f of x is 0. And at these hosts, f does not agree with what you get from the vector representation. And so you cannot do something like this. So the problem is, what are these hosts look like? If they have an arbitrary underlying structure, then maybe there is nothing we can do about it. But it turns out that if your language is balanced, then these hosts have very nice structures and actually allow us to do something similar to this. And one way to look into these hosts and understand the structure behind the host is to have a witness algorithm for this language capital F. Okay. And for this purpose, we can define the unweighted version of L. We call it gamma, and it's the most natural definition. X is in theta I if fi of x is positive. So every constraint function here has a corresponding predicate in the unweighted version. And it's in the predicate if and only if the function is positive. And the reason why this language, unweighted language gamma, is interesting because you can show that if L is balanced, then gamma is strongly rectangular. You cannot prove gamma is also strongly balanced. That's not true, but you can show at least gamma is strongly rectangular. And remember earlier we said if you have an unweighted language and you know it's strongly rectangular, then we have an algorithm, polynomial time algorithms, to solve the witness problem defined by this unweighted language. And now I claim that this algorithm immediately gives us a polynomial time algorithm for the witness problem defined by L. So it's essentially the same problem. We have an instance, and we can fix a subset of variables in any way we want. And we ask if there exists an assignment for the rest of the variables so that f evaluates to be positive. And it's just very simple reduction. Suppose we have this input with n variables and constraints over these variables, then you simply replace these functions by their corresponding predicates, and then you throw this problem to the unweighted witness problem and ask the algorithm there to find you, a solution. And this gives us an algorithm for the weighted language for the witness defined by problem defined by L. Okay. So from now on, we can, if we are given an input instance, we can fix any subset of variables, and we can ask, is there a way to complete the rest of the variables so that f evaluates to be positive? Okay. So these are the two ingredients we need. And here is the algorithm. First of all, we assume we already have this vector representation, these vectors SIs for the input capital F. And the algorithm goes by finding in polynomial time a new sequence of vectors. So we call these vectors Tn, Tn minus 1, because we're going to construct Tn first and then Tn minus 1. And these vectors has this very nice, very, very nice property. And we're going to prove this property inductively. So the property says that you can pick any assignment U. The only condition I have is f of u is positive. So U is not a whole. And then you pick any index k, and we get this equation. The left-hand side of this equation is you just fix the first k variables to be u1 up to uk, and you sum over the rest of the variables. And the right-hand side is really simple. It's just the product of these n numbers given to you by these s vectors and these t vectors. And the really intriguing part of this equation is that the left-hand side only depends on u1 up to uk. It has nothing to do with, for example, uk plus 1, uk plus 2. But the right-hand side depends on all the n entries of u. So if this is the case, then the following is easy to do. So suppose I fix the first k variables to be u1 up to uk, and I ask you to compute this exponential sum for me. Then I can pick any u with prefix being u1 up to uk, and fu is positive. If I can find such a u, then I can use this equation to evaluate the right-hand side, and I will get the answer to this exponential sum. And you can pick any u you want as long as they have the same prefix u1 up to uk. And once you have this property, it's just trivial to solve the problem. You just use the witness algorithm to find an assignment u such that fu is positive. If the witness algorithm tells no such a tuple exists, then of course we should output 1, output 0. Otherwise, we can set k to be 0, and we get this equation. We can evaluate the right-hand side very efficiently and get what we want.
So this means S1 over T1 is a constant or something, because the answer doesn't depend on you.
Yeah, it means this is a constant. Each of them may not be a constant.
So where did you use strong regularity?
We'll use it in the construction of T, or these vectors T.
Okay, so that's
So,
the magic.
so far, yeah, so far the balance only tells you have this vector representation, S. But I just say we're going to find T, but we're going to show how to find T. Why such these vectors T exist. And this will use a lot of balance condition. So let's start with the construction of T sub n, the simplest one. And the idea is we're going to look at the following matrix. Let's call it matrix M. the rows of this matrix is indexed by all these n-1 tuples. And the column is indexed by V, which is simply an element in the domain set. So this is the matrix that I mentioned earlier, which has exponential many rows, but only constant many columns. And here is how we use the balance condition. By the balance condition, we know that because the language is balanced, this matrix should be block rank 1.
So is n the instance size or the arity of the constraint?
This n?
Yeah.
Yeah, this is the input size, so it's huge. So you cannot hope to write down the matrix
But
explicitly.
the definition of balance was for.
It works for any instance.
Oh.
Yeah, that's why this is a really strong condition. It asks you to, you can pick any instance. N is the input size, and you can pick, any partition you want. In particular, here we pick, the first part to be the first n-1 variables, second part to be xn, and the third part is empty. And by balance, you know that this matrix is block rank 1.
Oh, so that's why
Yeah.
you comment about decidable.
So that's why it's not clear why this problem is decidable. So we know that this matrix looks like this, which has blocks, and all these blocks are rank 1. But because we have exponential many rows, you have no idea how these blocks look like. And the first step is that, okay, even though we do not know how this matrix look like, we can use the witness algorithm to compute some information about these blocks. And more exactly, we can find out the column set of each block. Remember, the column set is really small because we only have totally d constant many columns. And the algorithm is the following. Suppose I want to look at, let's say, column 1, and I want to find the columns that lie in the same block with column 1. And then first of all, you use the witness algorithm and to find an n-1 tuple u such that f of u1 is positive. If the algorithm says we don't have such a u, then essentially it means that the whole column of the first column is completely 0. And of course, this column is not in any of the blocks. That's the simple case. So suppose the algorithm actually returns a column, let's say this one, column u, row u. Then we just iterate over all other columns, column 2, column 3, and we ask, is f u2 is positive or not? Is f u3 is positive or not? Okay, so we know that u1 is already known to be positive. Then we ask, is u2 positive or not? If it's positive, then 2 and 1 is in the same block. Okay. So in this way, we can completely decide the column sets of all these blocks. And let's say Ci is the column set of block I. You can name the blocks in any way you want. And now we have the construction of Tn is the following. So you pick any element V in the domain set. And first of all, if column V is the 0 vector, then we simply set it to be 0. Otherwise, if V is in one of the blocks, so let's say V is in block 2, then T sub n of V is simply the V's entry of Sn, but normalized by all the entries in this block. So this is the column set of this block. Then we just sum all the Sn entries in this block, and we divide Sn of V, and we get this Tm vector. Okay. And here is the proof why this gives you the right T sub n. So suppose we pick a tuple starting with u1 to un minus 1 and v. And let's say it's positive. Now we want to look at this sum over all possible x, fixing the first n minus 1 variables. First of all, because this f of uv is positive, we know that v must be in one of the blocks. If v is not in any block, then the whole column of v is 0, then this cannot be positive. So let's say v is in block I. Let's say v is here. Then because f uv is positive, we know that u is a row of this block. Okay? So u is somewhere here. Now we can replace this sum over d to this sum over ci because we know that u is in block I. Then all these entries are 0 except the columns in ci. We also know that if x in ci, then this actually is positive because of the definition of the block. And we can replace by the vector what we get from the vector representation. And then we take all these out, and it becomes a sum over ci, and this can be replaced by Sn of v divided by Tn of v, just by the construction of Tn. So this gives us the vector Tn. And for the rest of the vectors, it's just very simple induction, and the argument is very similar. For example, suppose we want to construct tk, and we can assume that we already get tk plus 1 up to Tn. And the inductive hypothesis is that if you fix the first k variables and the sum over the rest of the variables, then it has this very nice explicit form. Now, we define the following matrix. Again, the rows are indexed by many variables, u1 up to uk minus 1, and the columns are indexed by v. And we define the uv entry to be the sum of the rest of the variables. So before we move to this next slide, the first thing should be noticed here is that this is exactly the same as what we have here. So although this is a huge matrix with exponential many rows, every entry I can evaluate very efficiently using this very explicit form. And also because the language is balanced, the matrix is block rank 1, which looks like this. And again, by using the witness algorithm in a very similar way, we can actually compute the block sets, the column sets of each block. And here we need one more thing. So we need the column set C1, C2, C3 of each block. But here, in addition to this, we also need to find one of the rows of each block. So you can use the witness algorithm to find a row, let's say u1 star in block 1, u2 star in block 2, and so on and so forth. And then you just do the same construction of tk. The interesting case is when this v is in one of the blocks, then tk sub tk of v is just, let's say this is v, then tk of v is just this entry divided by the sum of entries on this row, on this ui star row. And you can prove in a very, very similar way that now if you sum over these variables, you can actually finally get this very explicit form.
But why does it make sense to take an arbitrary row?
Yeah, the arbitrary row here, yeah, it doesn't make that much sense, but the only reason it works is because it's rank 1. So if I pick a different row, for example, I pick, let's say, U2. U2 is in the same block with U2 star, but it's different from U2 star. Then we know that these two rows are actually linearly dependent. And that's very useful in proving this equation, even though the definition of TK is from this very specific row UI star.
Well, I mean, each is multiple of the other, so you just got a constant in the numerator and a constant in the
Yeah.
denominator, right?
Yeah.
That's
Yeah.
because of normalization.
Yeah. So I'll skip this slide. So finally, I want to say something about the hardness part. I want to show you why it's actually very easy. So suppose we have a language L is not balanced. And what does this mean? This means there exists an instance and a partition so that the matrix derived from this instance and this partition is not block rank 1. And then you can define the following matrix A. You just multiply transpose of M with M, and you can show that A is symmetric, non-negative, and it's not block rank 1. Now you can use the result of Bulletoff and Grove, and the result tells you that the CSP defined by this matrix A is sharply hard. So the only thing left is to get a reduction from this to L, and you can use the instance that gives you this capital M as a gadget to finish the reduction. So the hardness part is half a page proof. So open problems. The first problem I think that is very fascinating is to get a dichotomy for counting CSP with more general entries with real or even complex numbers. And the interesting settings are, for example, constraint functions with +1, -1, or roots of unities. And the reason why this is interesting is because we are going to find a lot more tractable cases because we get cancellation once we have +-1 and get all these roots of unities. I personally feel that this seemed to be very hopeful given what we know so far. So we already have a dichotomy for a single symmetric real matrices. And we also have a dichotomy for symmetric complex matrices. And in this talk, we get a non-negative dichotomy. So I feel like we already have all the pieces there. And in particular, I feel that we already have collected all the algorithmic and complexity theoretic elements in order to prove the dichotomy for real or even complex weights. But putting everything together seems to be really difficult. And the second direction is about approximate counting. So suppose you have these non-negative weighted languages, and again you want to compute the sum, this exponential sum. But instead of computing exactly, you want to just output a number that approximates this. And it turns out that we know very little along this direction. So here is a paper from 2003, and even for the case when you have one single matrix, 2x2 matrix, and this matrix is symmetric, non-negative, we know very little. So to explain this picture, suppose you have a 2x2 symmetric matrix. Essentially, you have 3 free variables. Now, if you fix the off-diagonal entry to be 1, then essentially you have 2 variables. So it's 1, 1, beta, gamma. Okay? So this is the result in this paper where you have these 4 regions. And these 3 regions are shown to be easy. They gave a fully polynomial time randomized approximation scheme. And for this part, the black area, it's shown to be hard. Maybe you cannot see the words here. And for these gray parts, we don't know what's going on there. So even for this very simple case, there is still a lot of interesting questions, and we are very, very far away from getting a dichotomy theorem. So thanks very much.